Okay. Um, Now, one very important thing that I want to let you know about. Um, I have created test one. Um, it has six problems on it, chosen uh, from the homeworks for chapter one. Um, and uh, so the test is, and I want to make sure that I have this right. The test will be available for viewing um, in Pearson on in 1 week. So on September 21st, it will show up. Um, there will be a password. I will send a Canvas message to everyone that has a password. The password is just to protect you against accidental entry before you're ready to take it. But for some reason, Pearson is not letting me in. Let's try this again. Yeah, sometimes I try to go into to Pearson and it says, we can't open your course, and so then I just try it again and it lets me in. Um, okay, silent manager. The test is um, allotted the same amount of time as a class period, so 1 hour and 15 minutes. Based on the data that Pearson gives me about how long these problems take, the ones that I chose, it should definitely be possible to finish the problems within that span of time. Okay, so I've made the test due on Friday, September 25th at 11:59 p.m. So that's shown up in Pearson already. I've also made a practice test. That's a duplicate of a real one. That should be visible now. So you can take a sneak peek at that. If you go into Pearson and you do not see the practice test there, please let me know. But it should be there. Okay. The other thing is okay. So today I will cover the last new material that goes on that test. Wednesday will be a review, so I'll just be um, so I'll just be talking about the different types of problems and how there's general ideas for working those out. Okay, I see something in the chat here. No, the practice test um, does not count for a grade. So now it's optional and highly recommended. Now, one thing I had to do because I wanted to make sure that the test doesn't count for a grade, but Pierce, when I created the practice test, it required me to assign it to some kind of category, and I didn't really want to do that because it's not part of a grade. So here's what I did, and I believe it should work. That I categorized the practice. So for the whole course, all of your homeworks count 25%. And then the two tests and final, so free tests and all, count for 25% each. And that completely determines your grade. So in Pearson, the only types of assignments that count for a grade are homework and test. There is another category of assignment, quiz. So I made the practice test a quiz, and quizzes count for 0% of your grade. So, and I also, the other thing is I also set up the practice test so that you can attempt it multiple times. So if there seems to be anything off about that, like if it's not behaving like I said it should, or if it's doing something really weird, like actually counting it towards your grade in any kind of detrimental way, let me know immediately and I will fix it. But yeah, the practice test is just for practice. Okay. So around Monday, next Monday, watch your Canvas messages, and you'll receive one from me that has a password. Okay. So now to get through the last new material. Okay. Last time we saw linear transformations, which can a linear transformation can be used to transform vectors of any kind from one space to vectors of any kind in another space. In this class, we're only dealing with linear transformations, so far anyway, we're only dealing with linear transformations that transform, you could say, ordinary vectors, so points in n-dimensional space. So you can have a linear transformation that has n input variables that are real numbers, so it's a vector of size n, to vectors in m-dimensional space, where m and n are not necessarily the same. So in that setting, a linear transformation essentially is matrix vector multiplication. So your input vector x, you're multiplying by some matrix A. So what you're going to see in this section basically formalizes that idea that any linear transformation from one vector space to another can be described using a matrix. So if you have n input variables and m outputs, then the linear transformation can be described by m by n matrix. So we're going to talk about, if you're given a certain linear transformation, what is its matrix, and then we can use the matrix to determine certain properties of the linear transformation. All right, now I have to define some things for you to be able to talk about the matrix of a linear transformation, and we begin with one very important matrix, really the most important matrix of all. And what we'll be seeing in other times during the semester too, is the identity matrix. Now, the identity matrix, you can think of it as a generalization to matrices of the number one. The number one is the multiplicative identity element. So for any real number, x, 1 times x is equal to x. So here we have the same idea applied to vectors in n-dimensional space. Now the identity matrix has to be a square matrix, same number of rows and columns, and the entries are down the main diagonal. So from upper left to lower right, this is the entries here that have the same row and column indices. Like this is a 1-1 entry, 2-2 entry, and so forth, down to the n entry. Those are all equal to 1. Every other entry is 0. So that is the identity matrix. So you multiply any vector x by the identity matrix, it just gives you that vector back. So this is your multiplicative identity for n-dimensional space. All right. Now, these vectors we've recently seen. These are the columns of the identity matrix. And they have a property that these vectors, E1, E2, up to En, all the elements are 0, except for one of them that is equal to 1. So these vectors, okay. And I'll give you the other term for them, whoops. What is it doing? Okay. So these are also known as the standard basis vectors. for Rn. Okay. And here we see all elements are 0 except E1 has a 1 in the first position, E2 has a 1 in the second position, and so on. You slap these together. In this example, you get the 4x4 identity matrix. Those of you who are informally more physicsy, in three-dimensional case, these are the vectors I, j, and k. Okay, now these columns of identity, these standard basis vectors, are then helpful for describing the standard matrix of a linear transformation. So if you have any linear transformation, and notice here we have n inputs, m outputs, then to get the standard matrix, what you do is you apply the transformation to each column of the identity matrix. So T of E1 is the first column, T of E2 is the second column, and so on. So once you do that, then you put these results together as columns of a matrix, and that is your matrix A, and that is a standard matrix of the transformation T. And the reason why this matrix is useful is now, suppose I'm applying this transformation to some vector x. Now, I can describe x in terms of these standard basis vectors. Because if you look at this example here, if I have any vector x1, x2, x3, x4, it's x1 in the first position plus x2 in the second position, and so on. So I can write it this way. So any vector in n-dimensional space can be broken down as this linear combination of the standard basis vectors. Now, here's where I use the fact that T is a linear transformation, because T applied to this sum is the same as applying T to each term individually. So that's how linear, that's what defining properties of a linear transformation, that T applied to a sum is the same as sum applied to T. So I can take T of these vectors individually and add them up. Also, x1, x2, and so forth, these x's, they're constants, they're scaling factors. You can pull them out. So I can apply T to each of the standard basis vectors individually, and then multiply them by x1, x2, and so forth, add them up, and get the same result, because it's linear. But this is the same as a matrix vector product that we've seen before when working with the vector equation of a linear system. So T1, TV2, etc. Those are the columns of a matrix, and then these components go into the vector you're multiplying by. But this is A. This is a standard matrix of a linear transformation. So any linear transformation from n-dimensional space to m-dimensional space is equal to a matrix vector product. And the matrix involved is the matrix of a linear transformation that you get by applying your transformation to all the columns of identity. So if you're just given a formula for T, that's how you get the matrix. Just apply it to each of these vectors. And I will show you that in the first of these problems. So in this first one, you're given T in this manner. You're told what T does to each of a standard basis vector. So notice that T maps three-dimensional space into two-dimensional space. So you're applying T to three-dimensional vectors, E1, E2, E3. The output is a vector of length 2. Okay. So that means it's going to be a 2 by 3 matrix, 2 rows, 3 columns. So I can use the definition of a standard matrix with the information that I'm given. So I have, oh, missing a parenthesis here. Okay. Oh, and here too. All right. So first, we look at what does t apply to each of these. Now, in some problems, you might be given t in a different way. Like you might be given a formula for t, and then you have to work these out: t of e1, t of e2, t of e3. But here we're given to you. So now, t of e1, 1, 4, that's the first column. And then minus 8, 3. T of e2, second column. And then t of e3 is this vector 4 minus 2, third column. And that's it. You're done. That's the matrix. So you just stack the columns side by side. Okay. Now, here, same type of problem, the same thing is being asked for. You're still asked for the standard matrix of the linear transformation T, but now T is described differently. It is a transformation that rotates points about the origin through a specified angle. So how do you get the standard matrix in that case? Well, fortunately, there's a nice formula that provides it. Okay. So if your transformation is described in this manner, that it rotates points through a given angle, then here's the matrix. That comes from the cosine and sine, of that angle. So you just set up this matrix. So now one thing that is not really made clear in the problem, but I'll make it clear now. And I'm really surprised actually that they didn't specify it. The direction of a rotation, it could be clockwise or counterclockwise. What they're doing in terms of formulating these problems is counterclockwise. Now, I wish they'd actually said that, because you might think, well, as you go around the circle, like know your angles of 0 radians, pi over 3, or pi over 6, pi over 2, pi over 3, and so on. Then those angles are laid out in a counterclockwise direction, so it's kind of natural. But yeah, it would have been helpful if they had actually said that, because you could define rotations either way. Like if I take this matrix, this handles counterclockwise rotation through the angle theta. If I want clockwise rotation, I'd take the minus and move it down here, and that would take care of it. So what I actually had to do was, when looking at these problems, I had to look at what they're getting for the answers and use that to infer that they meant counterclockwise. Okay. So now that you have this rotation matrix, all you have to do is fill in the angle and work out the sine and cosine of that angle. So it'd be cosine and sine of 3 pi over 2. Cosine of 3 pi over 2 is 0, and sine of 3 pi over 2 is minus 1. But we have a minus here, so this is a matrix that does it. Well, it's worth pointing out that this first column, 0, minus 1, that is what you would get by rotating the vector 1, 0, because that's the first column of identity. So in other words, if I have a point 1, 0, that's a point that sits on the positive x-axis. So then I take that point, the positive x-axis, and rotate it 3 pi over 2 radians. Where am I going to be at? I'm going to be on the negative y-axis, and it's this point 0, minus 1. Similarly, if I take the point 0, 1, that's a positive y-axis. So that's also the vector e2, that's the second column of identity. And then I rotate that 3 pi over 2 radians. I'm going to be sitting at the positive x-axis, and that's the point 1, 0. Okay, so this formula will handle rotation matrices. Now, this next one, same idea, but there's a rotation involved, but there's something else. After you rotate, then points are reflected through the horizontal x1 axis, or geometrically, you can think of it as the x-axis, since that's a horizontal axis. So if you have a point in the xy plane, and you reflect it through the x-axis, what does that mean? It negates the y component. So if you were to draw a picture of like an xy plane, and you just draw a point wherever, and you reflect it across the x-axis, so that reflection is going to have the same x-coordinate, but now the y-coordinate will be on the opposite side of the x-axis. So that reflection has the effect. That's why it has the effect of negating the y component. So that's something you can take into account. But first, you handle the rotation, because notice it says it first rotates through this angle, then does the reflection. So order is important. That affects the result. So first, if you repeat what was done here, and work out the rotation matrix for a minus 4 pi over 3. So that is this matrix, but then these angles have to be worked out. And what you get is that, just from evaluating sine and cosine at these angles. Although the angle minus 4 pi over 3 is the same as the angle positive 2 pi over 3, just because of periodicity. Now, so what you would do is, this column is how transformation acts on E1, first column identity. This vector is the result of applying a transformation to E2. What you want to do in either case is negate the y component. So in other words, the elements in the second row now have to be negated. And that's all that's done here, is I take its exact same matrix and I just negate every element in the second row. So when this transformation is applied to any vector, it does a rotation, and then we negate y. I should point out that if this were to go in the opposite order, so here it says first rotate through this angle, then reflect across the x-axis. If it had gone the other way, so I'll just show that here. So reflection only has this matrix. So we have so for now, if you're taking the point that's sitting on the x-axis and you reflect, if it's already on the x-axis, it won't do anything. Well, it won't have any effect. So its action on the x-axis is you're still sitting on the x-axis. On the other hand, if you take a different point, a point that's sitting on the positive y-axis, and then you reflect it across the x-axis, like I said earlier, that negates the y component. Now, this also has its y component negated. It's set at 0, so it doesn't change anything. Okay. So after you just do the reflection, this is your matrix. But then what will happen is because this second column is negated, so now so if I apply the rotation to these columns, what's going to happen is because this second column is negated, the second column of the result will be negated too. So what you will get is all right. So if I take this matrix and negate the second column instead of the second row, so this entry will now be positive. That's positive, and okay, and that's positive. So this is the matrix in this case. So the diagonal entries are actually the okay. Well, I should make sure. Okay. Yep. Okay. So these entries are the opposite signs of what they were in the other matrix. So this is why the order of operations is important, and it'll be easier to convey that later when we talk about multiplying matrices, which we haven't dealt with yet. But really, what you can see what's happening here is that this is the standard matrix of just for rotation, and that's applied to E1 and E2. It's just that now, if you do a reflection first, now you're applying that rotation to minus E2, and that's why this second column is negated compared to this one. All right. Questions about that? Okay. Now, here we have a transformation. So transform vectors in 4-dimensional space. We have 4 components here to 4-dimensional space, because when you look at the result, we have 1, 2, 3, 4 components. So if it is possible to describe this transformation as a matrix vector product, then we can conclude that's a linear transformation. So that's really what this problem and the next one are about. So what happens is actually, I'm probably going to have to put this onto a new page. Okay. So here's another way that I can describe linear transformation. It's easier to write as a column vector, because then it makes it easier to express as a matrix vector product, because when you have a matrix vector product, the vector in that case is a column vector, and the product is a column vector. So here I'm just rewriting it in that form. So now what I can do is I can write this as a sum of vectors dealing with the components x1, x2, x3, and x4. Well, there is no x3 in here. All right, so now if I start doing that, so I break this into a sum of 4 terms. First one has all the x1s, this has all the x2s, all the x3s, of which there are none, and then all the x4s. So I'm just separating those x's. Next, I factor these x's out of each vector. That's right off to the side. So I have x1 times that vector. Okay. And in case x3 is just multiplied by the 0 vector. But now I can describe this as a matrix vector product where the vector is x1, x2, x3, x4, and the matrix comes from using these as columns. Okay. So there I put up columns together, and that is multiplied by the vector x1, x2, x3, x4. So this matrix times this vector equals this. And since I'm able to describe the whole transformation as a matrix times a vector, then it is a linear transformation. So if there had been some other terms like, x2 squared, something like that, then I would not be able to describe it as a matrix vector product involving just plain old x1, x2, x3, x4. So it has to be able to be something in this form where all you're doing with the x's is you're multiplying them by constants and adding them up. So if it's not something like that, it's not a linear transformation. Right, so just to summarize, this is the matrix involved. So this is the standard matrix of this linear transformation. And the column of zeros here is just because this transformation doesn't actually rely on x3. It's whatever value it is, plays no role. Okay. Now, this problem works the same way. We just have a linear transformation from 3-dimensional to 2-dimensional space. So notice there are only 2 outputs. Here's the first one. Here's the second one. So what this transformation does involving x1, x2, x3, that describes the matrix of a transformation. So if you look back at what was done in the previous problem, where whatever's done to x1, x2, x3, x4 ends up defining the standard matrix of that transformation. So you can see how the coefficients of the x's here determine what the matrix is down here. So now if we look at the next problem, you can use these to fill in the matrix. And you would actually, the way it's written here, you would find it easier to describe the matrix because you can tell me what the matrix is by going column by column or row by row. The way this transformation is written, it's actually easier to go row by row. So can anyone tell me, based on looking at this, what the matrix of this transformation would be? So it's a matrix of 2 rows, 3 columns.
Sir,
Yeah.
would that be 1 minus 8, 5, the first row?
Yes.
And then the second one, 0, 1, minus 2.
Yes, it is. Yeah, so the coefficients in each component give you the rows of this matrix. And you can see that from a previous one. Here we have 1 and 8 for x1 and x2, and there's nothing for x3 and x4. So that's why the first row is 1, 8, 0, 0. So to see it worked out in the same way as it was in the previous problem. All right, so here it's written out in a column vector form, just because it's easier to work with. And there too, you can separate it by which components of x are involved. And here we're getting it column by column, but then once you do, we see that the coefficients that we get, 1, minus 8, 5, match the coefficients of the x's in the first row. Second component matches what's in the second row. Okay, yeah, it's multiplied by this vector, so that's A times x, where A is this matrix. And as a summary, yeah, this is a matrix here that you just read off. Okay. Now, these last problems deal with certain properties of linear transformation that having a matrix can help you determine if the transformation has these properties or not. If any of you have taken, those of you who are math majors, taken modern algebra 423, you would have encountered these properties already for more general or more general transformations than this. But matrices are good examples. In the physics class that you'll be taking later, then this is kind of a preview of something from that class. So what does it mean for a linear transformation to be one-to-one or onto? So I have to define those concepts first. Okay, so transformation is one-to-one. We also say it's injective if it has this property, that the only way to get the same output value is to have the same input value. So, and just because a linear transformation is a function, for every x, there's only one y. That's just how any old function behaves. But for a one-to-one transformation, the opposite is true also. For every y, there's only one x. And I want to point this out that so if you're going to take modern algebra someday, and you're given some kind of transformation, you have to prove whether it's one-to-one or not, then you're basically working with this definition. That's so what you can do is to show that that it is one-to-one. It's basically your framework that if these are equal, then these must be equal. Or you could go with the contrapositive. You could assume that these are not equal and show that these must not be equal. So that gives you a framework for proving something about the one-to-oneness of a transformation. Now, in the case of a linear transformation, because T is linear transformation, this is the same as A times x1. This is A times x2, where A is the standard matrix. So, so this would mean that if these are equal, then that means that A times x1 minus x2 is equal to the 0 vector. So the transformation is 1-to-1 if and only if this system, AX equals 0, has only the trivial solution. All right. So this comes from A. No, I don't want that. Oh, silly thing. All right. A times x1 minus x2 equals, it should be x1 minus x2 equals 0. Implies that x1 minus x2 equals a 0 vector. Okay. All right. So these conditions where we are equivalent to these, where transforming x1 is the same as multiplying x1 by a. So what does this say? If this implies this, it means that a times x equals 0 has only the trivial solution. So once we have a matrix, we can check if this is the case. So we're falling back on what we saw a few sections back about working with these kind of homogeneous systems. So how can we check if AX equals 0 has only the trivial solution? We row reduce it. We get the echelon form. And we check, is there a pivot position in every column? If so, then yes, this has only the trivial solution and T is 1-to-1. So that's how you check 1-to-1ness. Get the matrix A, like it was done in previous problems. Row reduce it and check, is there a pivot position in every column? If so, yes, it's 1-to-1. Otherwise, it's not. Another characterization of 1-to-1ness is that A does not have free variables. Yet another characterization is that the columns are linearly independent. So all of these conditions are really saying the same thing. They're all equivalent. So if there's no free variable, that's the same as saying the columns are linearly independent. That's equivalent to saying that there's a pivot position in every column. That's equivalent to saying that AX equals 0 has only a trivial solution. That's also equivalent to saying that this linear transformation is 1-to-1. So all of these are equivalent statements. Just want to keep in mind when you see this problem in the homework that and the things they work into their answer choices, and they fall back on these different characterizations of 1-to-1ness. So that's one concept. Whether transformation is 1-to-1. It's also asking, does it have no free variables? The other concept is onto. What's that mean? So if we have a linear transformation, it's onto, and that's synonymous with surjective. And really all that means is that the range of a transformation is the entire space Rm. So in other words, any vector in the output space can be obtained by applying a transformation to some vector in the input space. So now suppose I have a matrix of its transformation, A. I'm saying that for any B, AX equals B has a solution. So the question we can ask is, once we get to matrix A, does AX equal B have a solution for every B? Well, for that, we again check the echelon form. Does it have a pivot position in every row? Another way of describing it is, do all the columns of a matrix span the output space Rm? Okay, but probably easiest to think of this in terms of pivot positions. So now we can talk about both concepts very concisely. So a transformation is one-to-one if its matrix has a pivot position in every column. Transformation is onto if the matrix of a transformation has a pivot position in every row. You can actually put the two terms together. Okay. So T is bijective. So that means it's one-to-one and onto. So it's both apply. If and only if the matrix of a transformation has a pivot position in every row and column. The only way this can possibly happen is A is a square matrix, and because AX equals B has a solution for every B, and the columns of A are linearly independent, then we can say that AX equals B has a unique solution. In Rn. Notice I had Rm before. Well, why is it Rn? Well, it is Rm, but M and N have to be equal. That would mean that the transformation is invertible, and so its matrix is invertible also. We'll talk more about inverses of matrices in a later chapter, and really, that's when a transformation is invertible. When it's both one-to-one and onto, then a transformation has an inverse. And what we'll learn later semester is, given a transformation and its accompanying matrix, how to get the inverse. Okay. These terms, injective, surjective, bijective, actually do not come up in the homework, but in so you're going to be dealing. Those of you who are math majors, if you deal with one-to-one onto, like in a class like modern algebra, you're going to come across these terms. So I wanted to make you aware of them. So now the question is this transformation that's given in a problem, is it invertible? No, sorry, is it one-to-one and onto? So you can form a matrix by looking at these expressions here that give you rows 1, 2, 3, and 4. So then we can examine that matrix. So we go ahead and get the matrix from a formula. Okay, and that's the matrix. Now we're interested in the echelon form of a matrix, and for that we need to get this in echelon form, not reduced echelon, just echelon. This calls for rearranging the rows. And this is what we get. We could do a row operation to get into this an echelon form, but there's really no need, because there's no way that this matrix is going to have a pivot position in every column. Why? Because where can you possibly have pivot positions? First column and third column, but not second column. There's no possible way because this one cannot be a pivot position because there's a non-zero entry to the left, and there's nothing else non-zero in this column. So the second column corresponds to a free variable, and if there are any free variables, it's not one-to-one. If I subtracted this row from this one, this row from this row would become zeros, and then we'd have echelon form, but it wasn't really necessary for this. And then finally, is it onto? Well, for that, you could use the same form and check, does it have a pivot position in every row? But it's not going to, because we have a row of entirely zeros. So once you have, if you've reduced a matrix, not necessarily to echelon form, but enough to see whether you get a pivot position in every row or every column, then you can answer these questions about whether it's one-to-one or onto. Questions there? These last two problems also deal with one-to-one and onto. Whoops, I didn't want to do that. Okay. Okay, so here we have a linear transformation described in a different way. T of E1, T of E2, and T of E3. These are the columns of your matrix. So then you go ahead and write down that matrix. All right, so then I filled in 1, 3, 2, minus 11, minus 3, 8 as the columns. Well, you don't even need to do anything. You don't even need to do a single row operation, because for one-to-one, you ask, is there a pivot position in every column? Well, you only have one pivot position per row, so you're only going to have at most 2 pivot positions. You're not going to have enough of them. So anytime you have fewer rows than columns, it's not going to be one-to-one. Right, so you need to have at least as many rows as columns. Now, what about onto? Even without performing a row operation, you can determine that there is going to be a pivot position in every row. Because what you could do is you could do a row operation to take a multiple of a first row and subtract from the second. And yes, you could go ahead and do that. But I can tell you as a shortcut, the reason why it's not necessary is the only way that's not going to be onto is if you do a row operation and this row turns out to be all zeros. The only way it's going to happen is if the second row is a multiple of the first, and that's definitely not true. I mean, if you're not sure, then you go ahead and perform a row operation and be sure that way. But so it's telling you what the outcome of that will be. You have a pivot position here and another one here. Pivot position in every row. It is onto. And finally, this transformation described using these formulas. Here we have 3 inputs, and again we have 2 outputs. And here we can readily define the standard matrix row by row. And the answer to one-to-one is immediate. Same thing. More columns and rows is not going to have a pivot position in every column. So it is not one-to-one. Another way of putting it is the columns are linearly dependent. That's another way of characterizing that the transformation cannot be one-to-one. And as for onto, it's actually already in echelon form. So from that, you can quickly see, oh, okay, there's a pivot position in every row. So it is onto. And I want to mention this is important for MyLab's answer choices that it's onto because the columns span the output space, which is R2. And that's equivalent to saying pivot position in every row. So questions about any of these? Or questions about any ongoing homework? Oh, okay. Well, I've come to the end of today's material. But I strongly encourage you to, when you're in MyLabs, look for that practice test, try it out. So then we can talk about it on Wednesday, and I'll be reviewing the different types of problems that will show up on the test. And just sort of, so it's a way of summarizing all the material so far and what you'll need to do with it on a test. So, okay, so I will stick around in case anybody does have any questions, and stop the recording at this point here. And the rest of you can scram.